Last year in Level 2 Mechanics, we looked at conservation of momentum in one dimension. This year, the step up for Level 3 Physics is to look at conservation of momentum, but this time in 2 dimensions. Here I have a video of 2 pucks colliding, a blue puck and a red puck. And next to them, or in the middle of them, there is a vector diagram. And these vectors show the momentums of each object. The blue vector represents the momentum of the blue puck, and the red vector represents the momentum of the red puck. And the green vector is the total momentum. You'll see that it's drawn so that it is the sum of the blue and the red vectors. Another thing hopefully you'll notice about the green vector is that it remains constant before and after the collision, which shows that the total momentum is conserved in 2 dimensions. Its horizontal component and its vertical component remain the same, even though the blue momentum vector and the red momentum vector are different before the collision and after the collision. Here's another way of analysing that same collision. This time I've got some graphs over the side here, and these graphs show the horizontal momentum of the red puck at the top and the horizontal momentum of the blue puck at the bottom. You'll notice that the red puck has no horizontal momentum before the collision, and then after the collision it jumps up to have quite a lot of horizontal momentum, and that matches what's happening to the motion of the red puck in the image. You'll also notice that the blue puck has a lot of horizontal momentum at the start, which then drops down to almost 0 horizontal momentum after the collision. The reason for this is that the blue puck has given its horizontal momentum to the red puck during the collision. And if we change over to look at the vertical components of the momentum for each of the pucks, you'll see that the same thing is happening. This time though, the red puck has a lot of vertical momentum at the start before the collision, and afterwards almost none. And then the reverse is the case for the blue puck. It has almost no vertical momentum at the start, and then after the collision it has a lot of vertical momentum. So the next thing we're going to look at is, why is that green vector there? It is the total momentum of the system, but why is it drawn where it is? On the right hand side there you've got a couple of graphs, and they show the horizontal displacement and the vertical displacement of that green dot. And that green dot represents this thing called centre of mass. And centre of mass is another useful tool for helping us to understand and analyse collisions. So we're going to have a look at our centre of mass now and what that is. The centre of mass of an object is where the total mass of the object acts as if it were concentrated. This is my daughter Nova's hammer. She got it for Christmas a couple of years ago to help build her treehouse. The centre of mass is sometimes called the centre of gravity, since it is where an object will balance, and the weight force can be thought to act through this point. I'm just going to mark the centre of mass of the hammer so we can visualise what the centre of gravity represents. You'll notice that the hammer balances on my finger if I put the centre of mass above it, but something even cooler happens if we throw the hammer. So here's me throwing the hammer, and I've tracked the handle of the hammer, the end of the handle, and that's not the centre of mass. And if you watch the tracks or the graphs on the right hand side, it doesn't really look like the handle of the hammer is in projectile motion. But something interesting happens if instead of tracking the handle, we track the centre of mass. Now this is the same throw, and now I'm tracking the centre of mass which I marked earlier. And you can tell by looking at the tracks as well as looking at the graphs on the right hand side that the centre of mass of the hammer is in projectile motion. And this is because the centre of mass is like the centre of gravity, and the weight force of the hammer is acting through that point. So that point travels as if it is in projectile motion. Now the centre of mass doesn't just have to be for one object. In physics it's often helpful to consider a system, and a system is made out of 2 or more objects. And we can analyse the system as if it was one object by using the center of mass of the system. And that system could be moving or that system could be stationary. So Nova, my eldest daughter, has kindly drawn us this picture here. And it's a system of two astronomical bodies. We've got Pluto, which used to be a planet and no longer is, and Charon, or Charon or whatever. Charon is the largest moon of Pluto. And I've chosen this system to look at how to work out the center of mass of the system because the moon Charon is quite large relative to Pluto, or compared to our Earth and our moon. And the way we can work out the position of the center of mass of the system is with this equation here, which is given to you. Here I'm just going to consider two masses. Mass 1 is Pluto, and its mass is given here. Mass 2 is Charon, and its mass is given here. You can just continue with this equation by adding on more and more objects until you've got all the objects in the universe, and you can work out the center of mass of our universe if you wanted to, but that'll probably take a bit of time. So I'm just going to do it for these two objects. Now you'll notice that the distance between these objects is taken from the object's center of mass. So the system is going to have a center of mass, and the two objects within the system also have centers of mass. So all I'm going to do is substitute in each of these values into this equation here. So here's the answer that I've got, and this is a distance, which is great. That's what you'd expect. So where's this distance measured from? So this position of the center of mass is relative to any object you want to choose. Now, usually you choose one of the objects within the system, which is what I've done. I chose to work out the distance or displacement of the center of mass from the largest object in the system, which is Pluto. So in here, for x1, the distance to Pluto from Pluto, I put in 0. So here I'm looking at how far the center of mass is from object 1, Pluto. So over here, when I'm working out the distance to object 2, x2, I put in the distance between
object 1, Pluto, and Charon.
And when I've calculated it, this is the answer I get. And this distance is about 10% of the way from Pluto towards Charon. Now I'm just going to exaggerate this a little bit. And I'm going to say that the center of mass is out here. What's interesting about this center of mass is that it is outside either of the two objects in the system. So that means that these two objects that make up the system actually orbit this point. Charon doesn't orbit Pluto, but both objects orbit around this point here, their center of mass. For the Earth-Moon system, the center of mass is within the Earth. Back to the Pluto and Charon system, this center of mass here is the point that orbits around the Sun. So systems are really helpful for considering multiple objects and how they move in relation to one another. And they're also really helpful when we look at collisions and explosions, and they give us another way to analyze collisions and explosions by looking at the center of mass of the system. So back to our pucks colliding again in this green dot. Hopefully now you can recognize that the green dot actually represents the center of mass of the system, and it shows us another useful way that we can analyze collisions and explosions. You'll notice that the green dot continues in a consistent direction at a consistent speed, which means it has a constant velocity, because in all collisions and explosions the center of mass of the system travels at a constant velocity. And the graphs on the right hand side show both the x and y components of the velocity of the center of mass, and you can see that they are straight lines, which shows that the velocity is constant. So what if in the collision or the explosion there are external forces acting? Well, that means that the center of mass does not travel at a constant velocity. And you can see that on this these graphs here on the right hand side, they're no longer linear. And the external force acting in this scenario is friction of the skittle and the ball on the floor. How you going, Nova?
Good.
What have you got there?
I've got this with Pluto here, and then Charon here.
Yeah. And what's Charon?
It's Pluto's moon.
Yeah, awesome. Thank you. Bye-bye.